Hello, today I would like to talk about modeling flow-induced noise using Fox-Williams-Hawkins formulation. In this tutorial, we will demonstrate how to model a 2D turbulent flow across a circular cylinder using LES, and we are going to also compute flow-induced noise using ANSYS Fluence acoustics model. This is the problem description. We have a turbulent air flowing over a 2D cylinder with a diameter of 1.9 centimeter, and we know that the free stream velocity is 69.2 meter per second, which will result in Reynolds number of about 90,000. The domain extends 5 times diameter upstream and 20 times diameter downstream of the cylinder. Let's start Fluent. I'm going to start Fluent in 2D with double precision option, and since we have 4 processors on this machine, I'm going to use the parallel option with 4 processors. After Fluent started, I'm going to read the mesh that I prepared before. Now that the mesh is loaded, we can take a look at the mesh by going under Results, Graphics, Mesh. I'm going to hit Save and Display. And I can take a look at the mesh quality to ensure that the minimum orthogonal quality is in acceptable range. Now, after verifying that the mesh orthogonal quality is acceptable, I would like to model the transient flow past this cylinder using the LES model. However, LES model is not available as a default option for 2D, but we can activate the LES model by typing the following command in the console. Hit enter. Now we can go to models. Under viscous models, we can use large eddy simulation, and under subgrid scale modeling, I'm going to use this Megaran Scan Lily option. Hit OK. And the solver will inform you that for scale resolving methods, bounded central differencing is the preferred method of discretization for momentum equations. And we can move on to the material properties of air. I'm going to maintain the default values for constant density and viscosity of air, and I'm going to move on to cell zone conditions. We can maintain the default setting for cell zone conditions, and we can move on to boundary conditions. On the boundary condition for inlet, I would like to change the velocity magnitude to 69.2 meter per second, and for fluctuating velocity algorithm, I'm going to ensure that the no perturbation options is selected. Hit OK, and we're going to maintain the default setting that we have for other boundary conditions, and we're going to move on to reference values. Under reference values, I'm going to compute from inlet, and I'm going to change the reference value for area and length based on the diameter of the cylinder, and I'm going to make sure that the velocity reference value is 69.2 meter per second, which is the velocity of the free stream at the inlet. Now we can move on to solution methods. Since we have transient flow simulation with incompressible fluid, we can use the non-iterative time advancement, and since we are interested in pressure fluctuations with higher level of accuracy, I'm going to use the second order implicit for the transient formulation, and for pressure velocity coupling, I can use the fractional step, and for pressure discretization scheme, I'm going to use the Presto. Now let's move on to controls. And I'm going to change the under relaxation factor for pressure from 1 to 0.7 to make the solution more stable. Under initialization, I'm going to make sure that the standard initialization from inlet is available. Now we can initialize the solution. Okay, now out of curiosity, I would like to know what would be the change in drag and lift coefficient on the cylinder in this transient flow simulation. So I'm going to go to solving. Under reports definition, I'm going to add the force report for drag, and we can repeat the same steps for lift forces. Now we can go to calculation activities, and for automatically saving the data, I'm going to change the interval to 20 time steps. Hit OK, and we can go to run calculations tab. And based on best practices for LES model, I know that the time step size should be 5e-6 for this domain. And I'm going to change the number of time steps to 4,000 time steps. Now everything is ready. We can calculate the simulation. After 4,000 time steps is complete, we can take a look at the lift coefficient to see how it was changing versus time. And also we can take a look at the drag coefficient to see how it was changing versus time. Now that the solution is complete, we are going to take a look at the pressure fluctuations in the domain using CFD Post. We can open the CFD Post and load the last file that was saved during our simulation and load the complete history as a single case file. Now we would like to plot the pressure fluctuations in the domain on the symmetry tube surface. I'm going to add a contour plot of pressure, and for the location I'm going to use the symmetry tube surface, and I'm going to hit apply. I'm going to change the view to see the best way of plotting the data, and by knowing that information we can go to time step selector and create an animation based on these time steps and hit play. You can see how the pressure is fluctuating in the domain, and by knowing this, the fact that the pressure is changing in the domain versus time, we can extract the acoustic noise based on the flow past the cylinder. Okay, we can use Fluent to extract the Aero Acoustics noise. In order to do that, I'm going to go back to Fluent, and under setting up physics, I'm going to go to acoustics models, and I'm going to use the Fox-Williams and Hawkins formulation, and I'm going to export the acoustic source data in an ASD format, and have in mind that the source correlation length has to be 0.095, and the acoustic noise will depend on the length scale that we are using for the source correlation in 2D format, but this problem does not exist in 3D calculations. Now we can define sources. I'm going to maintain the right frequency and the number of time steps per file as is. Hit apply, and we can define receivers. I'm going to introduce 2 receivers, and I'm going to change the coordinate for receiver 1 and 2 as follows. Now hit OK. Now we can calculate the simulation and export the acoustic noise at the location of receiver 1 and 2. After solution is complete, we can take a look at the acoustic signals to post-process the data that we got from the pressure fluctuations at the location of the receiver. Under acoustic signals, I'm going to use the wall cylinder as the active source zone, and I'm going to use all the receivers and also all the files that got saved during the calculations for the source data files. Now hit compute and write. After plotting the pressure fluctuation data that was received at the location of receiver 1 and 2, we can see that there is a lag between these 2 signals that is equivalent of the time that the pressure signal has to travel to reach the receiver 2's location. And also you can see the attenuation of the signal due to the distance that was traveled. Now we can use fast Fourier transformation to further analyze the signal. And you can see that at about a frequency of 900 Hz, we have the peak in sound pressure level that is occurring for location of receiver 1, which is consistent with the experimental data. Okay, this concludes our tutorial. Thanks for tuning in.